small singularities in fluid interfaces.
Thanks. So, well, thanks for the invitation. I see experts in the audience. I'm going to give a general talk. Okay. All right. First of all, this is the work of a team. So let me write down the team. Okay. Oh, not in alphabetical order. Wait a minute. Oh no. Yes. So I'm the only non-Spaniard in this group. Diego and his postdocs have been talking about these problems, got me interested. We solved a couple of problems. I'd like to tell you about it. So these are problems about fluid interfaces. So we have an interface either between two fluids. So there's some fluid here and some fluid there, or else there's a fluid here and let's say a vacuum up here. Okay, and this is what happens to begin with. The fluid interface. Oh, we're in 2 dimensions. We could be in 3 dimensions. I should talk at some point about what generalizations are easy and what generalizations are hard and which ones are probably wrong. But for the moment, we're in 2 dimensions, and our interface is the graph of a nice smooth function, and then we let the fluid do whatever it does. And it turns over, which means that the interface is no longer the graph of a function. Okay? And then once this happens, a singularity forms. Okay? And so for both of the 2 problems that I'm going to talk about, we're going to start like this. There will be then a turnover. Then there will be a singularity. Both of these problems are about incompressible fluids. Okay. The first of these problems is the water wave problem. So one usually says that there is water here and air up here, but I'm not going to say that. I'm going to stress that there is water here and a vacuum here. Okay, and what happens is simply the water evolves according to the 2D Euler equation, which is just F equals ma, Newton's law, in here. In the vacuum, there's no fluid, so there's no fluid velocity. The interface moves with the fluid velocity, and the pressure is, let's say, 0 on the boundary. That's one formulation of the water wave problem. Okay, I'll be a little more. Well, I'll be a lot more precise. But once that happens, then you might wonder what kind of a singularity forms, and the answer is the following. Okay, so for water waves, to start with, we have, let's say, a thing that looks like that, but I haven't drawn it very well. This is supposed to be the graph of a function, okay? And then at some later time, let's use the colored chalk. It looks like that. So it has turned over. It's no longer the graph of a function. And notice that this point is getting close to that point, okay? And then finally, at some crucial, at some particular moment of time, the curve intersects itself tangentially at one point. Okay, and so think of waves on a beach. This can easily happen, and so this thing meets that, and we call that a splash. And from that point on, the equations have no physically meaningful solution. I mean, water does something, but it doesn't solve the water wave equation. Okay, so this singularity forms in water waves. Okay, the other system that I want to talk about is the Muscat equation. This is a very, very equation. Okay, so let me describe a little bit the physics of the Muscat equation. So the Muscat equation describes two fluids in a porous medium. Think of oil and water in sand. Okay, so we have, let's see, which is heavier? Oil floats on water. So let's say we have water here and oil here, but they are in sand. So that alters the physics very greatly. It means that F equals ma is not true. I've lectured, I don't know, half a dozen times maybe on the Muscat problem, and I cannot resist bringing out one of my favorite quotes from literature. It's from War and Peace toward the end when Tolstoy is talking about the philosophy of history, and he says that we must seek to understand the laws of history which govern the affairs of mankind as surely as the physical world is governed by force equals mass times velocity. Okay, I thought this must be a peculiarity of the English translation I read. I don't speak Russian. I asked many Russians, is this in Tolstoy? And they all said, well, gee, I don't know. Maybe I'll take a look. No one got back to me. But one Russian finally got back. One Russian reacted differently and told me, you know, Tolstoy attended my university, and I'll bet it's in the original. And he looked it up, and it is. Okay. So, all right. So now, oil and water in sand obey not Newton but Tolstoy. Okay. So there is an experimental fact called Darcy's law, and Darcy's law says that the velocity of a fluid in a porous medium is proportional to the force that acts on it. The velocity, not the acceleration. All right. The proportionality constant is related to the viscosity of the fluid and to a constant called the porosity of the porous medium. I'm sorry? Permeability. I'm sorry, what did I say? The porosity? Permeability, thank you. I don't know what either word means. It's a coefficient in an equation to me. I am told that there are attempts to understand from first principles why it is true, and I am told that these attempts are not very successful, but I know nothing about that. For me, I just take the equations as given. The equations describe very strange physics. However, they do not describe merely oil and water in sand, but they also describe a Helly-Shaw cell. A Helly-Shaw cell consists of two parallel glass plates with the narrow space between them filled with, let's say, two fluids. These two fluids, let's say the plane is vertical, as I've shown. The plane is vertical. The two fluids, in effect, live in two dimensions, and their interaction with the plates by, I don't know, capillarity or something, is such that they obey the exact same equations as the oil and water in sand. Okay, so now, all right, so what happens? Well, for the Muscat problem, and sooner or later I should actually write down at least one equation, I promise I will. For the Muscat problem, there is a stable regime and an unstable regime. I'm only going to look at the simplest case in which the two fluids have the same viscosity but different densities. And since I'm claiming that something or other can happen, it's okay to make special assumptions. All right. Now, all right. So let's imagine that there's a heavy fluid and a light fluid. Let's imagine that the heavy fluid is underneath and the light fluid is on top. That is stable. And in that case, if you specify the interface at times 0. Then, as time moves forward, just on the level of some simple linear stability analysis for short time, one sees that everything looks good. Everything is stable. Okay? On the other hand, as time moves backwards from 0, everything looks ghastly. It's highly unstable. Okay? On the other hand, suppose that the heavy fluid is on top and the lighter fluid is on the bottom, and you specify the initial conditions at time 0. Then, if you want to know what happens for positive time, you're out of luck. It's highly unstable. But as time flows backward, the thing looks on the level of linear stability, looks perfectly all right. Everything looks fine. And one can, in fact, prove theorems that at least for a short time, everything is fine. Okay? This talk is about fluid interfaces that turn over. Let's imagine that the interface looks like this. All right, which of these will be the heavy fluid and which will be the light? Let's say this is the heavy fluid, and this is the light fluid. All right, then let's say if you put your finger here, the heavy fluid is on top of the light fluid locally. But if you put your finger here, the heavy fluid is underneath the light fluid locally. That means that as time flows forward, the thing looks highly unstable because of this picture, but as time flows backward, the thing looks highly unstable because of this picture, and therefore you are plainly and simply out of luck. All right? Now, what we're going to find is that there are solutions of the Muscat equation that start like this and in finite time behave like this. Notwithstanding what I just told you, the solution continues to exist for a finite time after it looks like this because of two words, real analyticity. Okay, think of the heat equation. That's not quite accurate, but it's the 0th approximation to what's going on. If you start with a nice smooth initial datum, then immediately when you solve the heat equation in the stable direction, the solution becomes real analytic. And now what is happening after as the fluid begins to turn over, it has picked up a certain amount of real analyticity from having been in the stable regime. And therefore, for reasons, thanks to some version of the Cauchy-Kovalevsky theorem, the solution continues to exist for some time going forward, even though it's highly unstable. Nevertheless, as one might guess from the idea that we've gone from the stable world into the Cauchy-Kovalevsky world, the solution is less and less stable as time flows forward, and real analyticity is lost. The strip of analyticity shrinks. Okay, and so this thing is in grave danger of forming a singularity, and in fact, infinite. So this happens on some open set of initial conditions. There is at least one initial condition at which there is one point at which smoothness is lost. And so there exists a solution which initially is like this, and let's say real analytic. It turns over in finite time so that it looks like this and is even more real analytic. Okay, but then as time continues to increase and this thing continues to turn over, all of a sudden, at one point, something bad happens, and this interface will be entirely real analytic, except here where it is C3 but not C4. And presumably, although we don't have a proof, presumably from that point on the equation has no more solutions. Okay, I think I should state the equations. I should write at least one equation on the blackboard. Yes, yes, there's a formal symmetry in the equation, yes. Yes. All right, so maybe I'll write down the water wave equation. All right. All right. So there is a region omega of t in the plane. T is time. This is the water. Outside the water is vacuum. Okay? All right. Now, in the water region, there is a velocity. So here, u is the velocity, and let's say p is the pressure. So p is a number. And these are defined only for x in omega of t. And outside, there is not air, there is vacuum. And if there's vacuum, there's no fluid, and therefore there's no velocity and no pressure. Okay. There is an interface. The boundary of omega is, let's say, parametrized as z of alpha t. Alpha is the parameter, t is time. So, all right. So these are the unknowns. What's the physics? Well, first of all, the velocity satisfies 2D Euler. And let's say here, let's put in gravity. Okay? The water is the water is incompressible, so the flow is divergence free. And all of that is happening in omega of t. Okay. Well, let's see what's happening on the boundary. The pressure is, let's say, 0. Well, pressure is only defined up to an additive function of time. The pressure is some function of time alone. Okay? That's, let's see, what can I say? All right, maybe I just state it. The physics of water would be very strange if that weren't true. Well, in fact, that isn't quite true because of surface tension. The fact that I'm asserting this on the boundary rather than something else means that I'm neglecting surface tension. So one might wonder, is there a version of the theorem that I just stated for water waves with surface tension? And I just got an email from Diego, in fact, I don't know, an hour and a half ago. The team has been working on it, and it seems that there is a version with surface tension, but I'm not going to talk about it. All right. So, so that's happening, and also the interface itself moves with the fluid. Which means that if you take this z of alpha t and take its time derivative, so that's something like the velocity, but only something like the velocity, that equals u of z of alpha t, that's where I am at the moment, and t, that's what time it is. But this isn't quite true because, well, I can add or subtract my favorite function of alpha and t times d alpha z of alpha and t. And the significance of this is that nobody told me which parameter to use, and I can simply change the parametrization of the interface as a function of time, and that has no physical meaning. And changing this coefficient c simply changes the parametrization of the interface without changing the interface itself. Okay? So these are the equations. These are the water wave equations. Okay. Now, a lot of people studied the water wave equations and their variants. I should say something about what was known. It's not going to be anything like a complete list, but I jotted down a few names and a few phrases. First of all, there are two famous papers of C.J. Wu from the year 2000 plus or minus a few, in which she proved that the water wave equation, the way I've stated it, is well posed in Sobolev spaces for short time. She did not have to assume, so both in 2 dimensions and in 3, okay? She did not have to assume that the interface was a graph, and notice this problem does not assume that the interface is a graph, but she does assume that the interface satisfies the chord arc condition. So here's an interface, and here are 2 points on the interface, and the chord arc condition says that if you draw the chord, then, and if you draw the arc, then the arc is not much longer than the chord, okay? All right, and so if you have a nice, smooth initial situation, and in particular, if the chord arc condition is satisfied, then for short time, the water wave equation is well posed in Sobolev spaces. So there is a nice, smooth solution, and no disasters happen. Now, of course, we're interested in the case in which we allege that there is a splash singularity. Oh, by the way, I forgot to mention a splat singularity. Let me take 1 minute and describe that. In the splat singularity, things start as before, but the collapse occurs along an arc rather than at a point. So here's an arc that this part of the water wave shares with that part of the water wave, and at some critical moment that happens, and if we looked a moment before that, what we would see is something like this, so that it has not yet closed and there is not yet a singularity. The point that I want to make is that as you approach either a splash or a splat, as long as you stop before the singularity occurs, the chord arc condition holds, but the constant in the chord arc condition is going to hell as you approach the singularity. And of course, at the singularity, the chord arc condition is not satisfied.
Are there examples of splat singularity?
I'm sorry?
Are there examples of splat singularity? Or it's just examples?
Examples. Well, I mean, there is a theorem. One of the theorems that we prove is that a splat can happen. There were numerical simulations showing that a graph, that a solution of the water wave equation can start as a graph and then turn over. That was seen from numerics, and the numerics looked very safe and very stable. But at a certain, after a while, but after the turnover, the numerics became unreliable. What I'm describing to you is the result of modified numerics using a trick that I hope to explain that keeps them accurate up to the splash. I should say, I realize that I've left a misleading impression. It sounds as if I said, perhaps I actually said, that we have a proof that a graph, that a solution of the water wave equation can begin as a smooth graph, then turn over, but remain smooth, and then form a splash. What we have is a reliable numerical simulation of that. We have a proof of the following. We have a proof that a water wave can start as a graph and turn over. And we have a proof that that a water wave can start close to but not at a splash, so like that. And in finite time, the splash the splash forms. Okay.
So the splash is your singularity?
The splash is the singularity.
I thought you had a singularity before the splash. That's what
Oh, okay. Wait. So, okay. So what is? All right. One can. All right. Do you consider the turnover to be a singularity or not? Let's not. Okay. No. Then until for water waves, the first thing that goes wrong is the splash. Until then, there is a turnover, but everything is nice and smooth. And
I thought you said there was something about C3 being...
that's for the Muscat. That's for the Muscat. Okay? Okay.
So the splash is your singularity.
So the splash is the singularity. Or the splat. Okay. All right, so I've stated the equations for the water waves. Let me state the equations for the Muscat. Okay?
solving and understanding doing analytical analysis on this equation.
Yes, yes. It might not be necessary, but picking a clever C makes it much simpler. Yes. But so that's an ingredient, but it isn't the main ingredient. I'll get to the main ingredient. Okay. So let's write down the equations. Let's write down the Muscat equations. And so I'm going to write down the Muscat equations for two fluids with the same viscosity and different densities, so not really oil and water, which I guess have different viscosities. All right, so here's an interface. The interface is z of alpha t again. T is time, and alpha is the parameterization of the interface. Okay, and there are two regions, let's say omega 1 of t and omega 2 of t, and the plane is subdivided into these regions, and this is the boundary between them. Okay, there's one fluid up here and another fluid down there. They are both incompressible, but they live in a porous medium. They are in sand or they're between glass plates or something, so that they satisfy the following weird equations. So let's see. Let's say ui, which is in ui is the fluid in region I. Okay, in region omega I is 1 or 2. We have velocity ui of xt and pressure pi of xt. Okay. Now, according to Darcy's law, physics a la Tolstoy, U is equal to ui is minus the gradient of the pressure minus, let's say, the acceleration of gravity, and then there is 0, and then there is rho sub I, the density of fluid I. Okay? So this is Darcy's law. Which is allegedly what experiment shows. Okay. The fluids are incompressible, so the divergence of ui is 0. So these things happen in omega I. Okay? And now what happens at the boundary? So at the common boundary, first of all, the pressures are equal. Okay? Then, secondly, if you compare the velocity of the two fluids, there is a jump across the boundary, but it is tangential. Okay? And finally, the interface moves with the fluid. And so I can say that using either velocity u1 or velocity u2, and it doesn't matter which because u1 minus u2 is tangential. And again, there are these funny functions c that don't mean anything but pertain only to the parametrization. Okay, so this is the Muscat problem. And so again, let us assume that initially that we have a graph, and initially the heavy fluid lies underneath and the light fluid lies on top, and time is flowing forward. Okay, and then again, it's for this problem that we have a turnover followed by the emergence of one single point at which the C infinity smoothness breaks down. So those are the results.
Well, as long as it remains a graph, is it okay, or does it have to be not a graph?
Oh, let's see. What's true and what can we prove? What's true, all right, I guess, is that as long as it's a graph, it's okay. Nobody has proven that. We haven't proven it either. So both for Muscat and for water waves, there's absolutely no claim that these singularities that we exhibit are the only singularities in the problem. Okay. So for instance, people have worried about singularities of water waves, and these don't, as far as I know, don't look like the singularities that people have worried about, and so they have nothing to say about our thing, and we have nothing to say about their thing. Okay. All right. How to prove any of this? Let's see. Let's start with water waves. In each case, one knows from the 19th century that if you're doing two-dimensional fluid dynamics, you really should use complex variables, and we will for both these problems. All right. So let's go back to water waves and think how we should try to understand the problem. Well, first of all, the equation for water waves is time reversal invariant. So if you make a movie of a water wave and run it backwards, it's still a water wave. And so what we can do is simply start with a splash singularity and hope that there is a solution of the problem in which the wave opens up. Okay? Now, let's take the known technology about water waves. This is a general lecture and not a highly specialized thing for experts. Let me just say it's a horrible mess. Okay, if you look at what people do about water waves, it's a horrible mess. However, there is a trick which converts the horrible mess that we face to the horrible mess faced by C.J. Wu. Okay, and once you see that, then you need luck, but there is luck. All right. So how shall we? All right. Well, first, all right. Notice simply that we cannot apply the known theorems because we are starting with a singular situation. In particular, we're starting with a situation in which the chord-arc condition fails. Okay, so we can't just apply the known theorems. Okay.
I'm sorry, but in the plane we can consider overlapping pieces of
Yes.
So
Yes.
From this side it is not a singularity. Yes, if we consider them locally. So they can overlap but don't notice.
So in fact, one can try to prove this theorem that way. We considered it. We used another method. That probably works. That probably works. There is the. I will explain. I will explain a little bit. But yes, one could consider the water wave to be a Riemann domain. Yes. Okay. All right. So here's. All right. So let's look at. Well, let's decide first. What are the independent variables? How shall we specify the velocity? The interface is simply z of alpha t. It's a function of alpha t. That's great. How about the velocity? Well, elementary potential theory gives lots and lots of ways to specify. Oh, I forgot to say our fluid is irrotational. I think I forgot to say that. The curl of U is 0. One can consider the rotational situation, but since I'm asserting that something can happen in the irrotational case, it can even more can it happen in the general case. All right. So okay. So all right. So we have our velocity U, and it is incompressible and irrotational. So of course, to specify, I mean, such a thing is essentially an analytic function. Okay, well, so how can we represent it? Well, we could represent it as the gradient of a scalar function. This is the velocity potential. And U admits that description simply because it's irrotational. Or we could decide that U is the gradient perpendicular of a stream function. Gradient perpendicular means minus d dx2 plus d dx1. And in general, if V is a vector, V1, V2, V perpendicular is minus V2 plus V1, rotation by 90 degrees. Okay? And U has that interpretation because it is divergence free. Okay? And phi and psi are conjugate harmonic functions. Okay. In particular, each one of them is individually a harmonic function. So those are standard ways to represent U. So now we have U, we have phi, and we have psi. That's all very nice, but these are defined only on omega of t, and we don't know what omega of t is. That's part of the problem. So this problem has the revolting feature that the unknown function lives on an unknown domain. Okay, so that's a complication. All right, well, one thing we could do is look, let's say, simply at the normal component of U on the boundary. So that's simply the dot product of U with, let's say, the inward pointing unit normal to the fluid. And from this, one can, of course, reconstruct U because U is divergence-free and irrotational. And so elementary potential theory says that it's enough to specify this. I'm cheating. I'm not telling you what happens at minus infinity or out. One imposes some conditions to make the solutions physically reasonable. Let's not worry about that. U is, for example, L2, so that the kinetic energy is finite. All right. In any event, specifying this is another way to specify U, and that has to do with potential theory on the domain omega of t. And nothing is wrong with omega of t as the chord arc condition fails. Here, for instance, there's absolutely nothing wrong with this domain from the point of view of potential theory. If we're trying to solve, let's say, the Neumann problem here, we should just remember that a function is allowed to take two values here, one as the limit from this side and the other as the limit from that side. But other than that, there's nothing wrong with potential theory. Okay, so those are nice ways to specify. There is yet another way, and there is something called the vorticity amplitude. And the vorticity amplitude is the thing which people actually use, well, many people actually use in order to state the water wave equation. Okay, so for x in the interior of omega of t, something like the Biot-Savart law tells you that you can represent U of x as so this thing is a function. Think of it as a function on the boundary, and to this we're applying the Biot-Savart law, and we are finding our U, which is then divergence-free and irrotational inside omega. As x tends to some boundary point z of alpha t, but x remains in omega of t, you have to take this limit carefully, and you find that on the boundary where it counts, U at z of alpha t, t is equal to 1/2 omega of alpha t times this thing, plus something called the Birkhoff Rod Integral at alpha t, where the Birkhoff Rod is a vector quantity which is defined as 1 over 2 pi integral z of alpha t minus z of beta t perpendicular over z of alpha t minus z of beta t squared omega beta t. These are divergent integrals. They're defined in the principal value sense. Yes, yes. Okay? All right.
These are the limits of what you get.
Exactly, exactly. So, you know, this looks very natural if you just plug in there, but you've got to tend to the limit carefully, and you get that. Then anyone who's thought about singular integrals is unsurprised. Okay, so all right, fine. Now this is what we're going to use, the vorticity amplitude. This is
So the
yeah.
velocity will be finite on this?
I'm sorry.
So the velocity will be finite from this integral, or?
Yes, yes. So if the omega is smooth, let's say, then this u is also smooth. And I mean, the omega, if the omega is, let's say, bounded, then this needn't be bounded, but it's, I mean, it's a borderline thing. This.
You mean that you will move away from the interface?
Oh, I'm thinking that u should be smooth up to the interface. Okay. Okay, and then omega will be smooth on the interface. Okay. Now here's the trick. In order, I mean, how do you see that u has such a representation? And the answer is you do elementary potential theory inside omega and elementary potential theory outside omega. Okay. Inside omega, nothing is going wrong when there is a splash. But outside omega, plenty is going wrong at a splash. The complement of omega is disconnected into that and that. It's a pathological situation. And so if you want to represent u this way, something goes wrong as you approach the splash. And indeed, our numerics show that omega grows as you approach the splash. It tends to infinity. It appears to tend to infinity like 1 over the time to the splash.
Is it true that omega in this case is something like the tangent component of velocity?
It's the okay. It is the difference between the tangent component of the velocity and the tangent component of some fictitious velocity that you define on the outside, even though the outside is a vacuum. Okay.
So, but how can we use it if we don't know omega?
Okay. That's an excellent question. I would ask you to wait 5 minutes and all will be revealed. Okay? All right. So, all right. So what people usually do is to take as the unknowns z of alpha t and omega of alpha t, okay, and try to solve the equation. And there is no way that that can work because omega is singular at the splash. Okay. Well, all right. So armed with that with those completely elementary remarks, now we're going to do a 19th century conformal mapping. So here's our water, and this either exactly touches or comes very close. Let's put the origin here. Let's slit the complex plane here, and let's pass from z to, let's say, z tilde equals the square root of z, a branch defined in the complex plane minus that slit. Here's the water, and when we pass to the square root, maybe this slit becomes a thing like that, and maybe we've got something like that. All of a sudden, nothing is wrong with this domain. Well, it goes out to infinity, but in fact, if you look at the actual paper, we're dealing with periodic things. We're dealing with a situation which is periodic of period 2 pi in the horizontal direction, so you don't really take the square root of z, you take the square root of tangent of z or something like that. And so in fact, what you find is that in fact this picture is compact and smooth, and absolutely nothing is wrong with it. Okay? Now, if I tell you z of alpha t, then I am telling you z tilde of alpha t. And these things are obviously completely equivalent. They carry the same information, and the smoothness of this is completely equivalent to the smoothness of that, except that here we think there might be a splash singularity, which means that these guys might touch the slip. So what? Okay? So there's that. All right. Now, there is u, which is, for example, gradient of phi, and phi is harmonic. Let's take phi, and let's define phi tilde in such a way that phi tilde of z tilde is equal to phi of z when z tilde is equal to the square root of z. So in other words, phi tilde of z tilde is, I guess, phi of z tilde squared, or whatever the analogous thing is when we use the square root of the tangent of z instead of square root of z. Okay? Phi being harmonic is exactly equivalent to phi tilde being harmonic. So now we have a harmonic function on this domain, which I'm going to call omega tilde of t. And this guy gives rise to a velocity, which I'm going to call u tilde of zt, z tilde t, and it's simply the gradient of phi tilde by definition. So that is, since this guy is harmonic, this guy is harmonic, this guy is the gradient of a harmonic function, it is incompressible and irrotational. Okay? Now, this u tilde is related to u by some trivial transformation law, which I'm not going to write down because I will get it wrong. Okay? But it's obvious that so far I've done absolutely nothing of significance. Anything I've done can be undone. This is so far just notation. But we're now going to look at this problem, and we're going to think of this velocity as being defined in terms of its vorticity density. So we're going to apply this representation not to u, but to u tilde. And that will give us a vorticity density that I'm going to call omega tilde of alpha t. Okay? Omega tilde of alpha t gives the same information as u tilde or phi tilde. Okay, it's another way of describing the problem. But to say that there is an omega tilde, this omega tilde, means that I have to do potential theory on this domain, capital omega tilde, and on its complement. But there's nothing wrong with this domain or its complement. And therefore, there is no problem defining the omega tilde. This thing satisfies the chord arc condition. And so one takes the water wave equation here, which is such a horrible mess that I don't want to inflict on you the statement of the equation in terms of these unknowns. I don't know if you've seen it before, but I promise you it's just awful. Unless you have a good memory, once you see the equation the first time, you will simply forget it. Okay. If you transform to these variables, there is a variant of the water wave equation with various Jacobian factors floating around. Yes, and so there is a variant of the water wave equation for this problem, for the tilde problem. All right. Once you have that problem, you can then pray that the techniques that solve the water wave equation also solve the tilde version of the water wave equation. There are a couple of particularly sneaky choices. You mentioned the function c. One picks a clever function c. That is not the same function that solves this. There is a slightly different function c. There are particular auxiliary functions and a very tricky, unmotivated energy. Not the physical energy, but some quantity which you hope, whose time derivative you hope you can control. And indeed, you find after many pages of calculations that you can control it because all the terms that you cannot control miraculously cancel. Okay. If you modify all of those tricky quantities in just the right way, all of the hard parts of the proof go over. There are some junk terms which can be controlled. The cleverness is to find the correct analogs of what was done for the original water wave equation. All right, what does that mean? That means that in the tilde domain, the equations that you've got can be solved for short time in Sobolev spaces. Well, you start with a splash over here. Let's say these guys exactly touch, then these guys exactly touch. There is a solution, and you then undo this simple conformal transformation, and what do you find? Well, one of two things can happen. Either these guys fly apart, or they interpenetrate. If they interpenetrate, then you have a perfectly good solution here, but it doesn't mean anything physically. It has nothing to do with what water actually does. On the other hand, if they fly apart, so in other words, if, for example, these guys are initially moving away from the slit, then these guys will initially move away from the slit, and in particular away from each other, and you get a physically meaningful solution of the water wave equation. So all that remains once you have done the hard work of seeing that this tilde equation can be solved is that you have to check that that one can specify initial conditions in such a way that these guys initially fly away from the interface. Why is that? Well, what could we specify as initial conditions? We could take the initial interface and the initial omega, tilde. Or we could take the initial interface and the initial normal component of the velocity. And those are equivalent descriptions. And so in the tilde world, in the original world, you're out of luck because the omega, which is what you're solving for when you solve the water wave equation, is bad news at the splash. But here, simply, there is no bad news. Any bad news that you might actually encounter will only come at the end when you apply the transformation. And so then specifying the initial omega is equivalent to specifying the initial normal component of the velocity in the tilde component, in the tilde coordinates. What constraints do you have? That can be anything in the appropriate Sobolev space. It had better integrate to 0 because we have a divergence-free thing, divergence-free velocity field. It had better integrate to 0, but that's the only constraint. And so once you decide that, once you simply pick an initial velocity field that's flowing this way at this point, this way at that point, and integrates to 0 along the boundary, then there is an omega tilde that corresponds to it, and that's the initial condition for which you solve the problem. Okay, now I'm afraid I've forgotten exactly which question you asked, but I hope I answered it.
Yeah.
Okay.
But formally, we can consider a case when this domain omega theta goes up, not down.
Oh, yes. So there's a perfectly good solution to this problem. The only question is, given that perfectly good solution to this problem, what does it correspond to here? Do you get a solution to this problem? Okay, so that's all right. Now I have all right. I'd like to stop at 3 o'clock. Am I right? That's the correct thing to do, to stop at 3 o'clock. I have 7 minutes to discuss the Muscat equation. Let me see what I can say about the Muscat equation in 7 minutes.
So the main trick here, just to review, is that you apply this conformal transformation.
Right.
And then, roughly speaking, you can use, then your chord condition is okay.
Right. Well,
but then you have other problems too, I suppose.
Well, yes. Well, so I would say there are two things. I mean, the conformal transformation, I think, would occur to anybody who was around for 19th century mathematics. But so what? And the thing to realize is that this omega tilde, everything else is just, for everything else, there's just a simple dictionary with the most elementary formulas. But there's this omega tilde, which is a genuinely new guy. And the correct things to solve for are the z tilde and the omega tilde. That's the point. Okay. 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 So.
The data cannot be arranged to make it into a graph.
I'm sorry?
The data cannot be arranged to lead to a graph, to produce a graph as a...
Probably. Probably. What a good question. Probably.
Because you said that you either start from a graph and the design is not a graph, or...
Oh, well, so, so this can start as a graph. Oh, maybe,
The original problem.
or for the original problem. All right, you know what? Let us declare that instead of discussing Muscat for the remaining 5 minutes, let me say a little bit about the plan to produce a proof that there's a graph that becomes a splash. Okay, so first of all, there is a computer simulation that looks very reliable in the sense that, let's say, if you use a much finer grid, you discover that to many decimal places nothing changes. So you start with a splash, with an exact splash singularity, and you run it backwards, and you discover that after 10 seconds you have a graph. Now, what do you really have? You then, your simulation gives you, it can easily be used to produce a function of functions of alpha and t. These functions are z tilde of alpha t and omega tilde of alpha t. And they do not solve the equations, the water wave equations, but if you write the water wave equations in the form stuff equals 0, then you discover that stuff is very small in your favorite function space norm, or at least you believe that. Okay. Now you want to prove a theorem. The theorem says, suppose that you have an initial condition and a solution up to some fixed time, and an alleged solution up to some fixed time. The alleged solution does not solve the equation exactly, but the stuff that is supposed to be 0 is instead very small in some function space norm. Close to that is an exact solution. That's a shadowing theorem, okay? All right, we have, the team has taken the trouble to prove a shadowing theorem for this problem. If you go through the proof of the shadowing theorem in revolting detail, you can produce explicit constants. How small does the function space norm have to be in order to get how good an approximation? Yes. Well, I mean, wait. We do means we plan. We hope to. Okay. I do not claim that we have done it. We have. I mean, there are things that we have done, but let me not get into exactly what they are. But the plan is to use that strategy to produce a computer-assisted proof that close to our computer simulation is an actual solution. That's the plan.
Shadow theorem is what we used to call inducer function theorem.
What's in a name? Okay. Okay.
In the picture you showed, suppose that we make this cut, or rather we just consider a ramified covering.
Yes.
Ramified at the point just inside that you showed.
Yes.
Then essentially we have just local isometry, right? I mean, because in your conformal map you just kind of spoil the metric, and that's why you have to
Right.
resolve this problem.
Right.
But this way, if you just think about two sheet cover, then you just keep the same metric, and then you just apply directly that theorem. Because the conditions they are just local.
All right. So I would say it's a natural idea. I imagine it can be made to work. It is slippery. Slippery means that in order to make it work, you need to be careful.
It looks like just the local
mean-
existence theorem would just have this.
So let's see. So what plays the role of the formula? Or what plays the role of this formula?
So, but now this becomes any values only on this double cover. Right?
Nevertheless, right? So there, all right. So there is a double cover, but there has to be. You have to write down some formula on the double cover, and argue about it. I guess so. I guess it can be made to work. I do not claim that this thing is the only thing that works. Indeed, I think that it is more natural to look at a Riemann domain. I think that is the first idea that one thinks of. But in order, again, I claim it is slippery. I think what I mean by slippery is try writing down a correct proof of which one can check the details. You're going to have to do some work. Okay. But well, all right. So I think then we agree. This can probably. I mean, you both thought of it. We thought of it too. I'm sure many people thought of it. It is not a walkover to make it work.
And the way you construct the split, you slightly perturb the one which has a splash.
Oh, no, we simply, the splat, we simply start with that and then run it backward. One thing I didn't mention is the real analytic case. In the real analytic case, the water wave equation is much less frightening. Simply, it is from some appropriate point of view, it's a first order equation. And so if you're only doing small time and real analytic solutions, there is some version of your favorite general version of Cauchy-Kovalevska will take care of it. And so, for example, if you simply want to produce an example of a splash singularity, you can declare that you start real analytic. Then you solve backwards. Now you have a real analytic thing. You solve forwards. And you have a real analytic thing which remains real analytic until the moment of the splash. Okay. However, if you want to make a splat, then you need to start with something where two functions agree on an interval but are not identical, and so that is not real analytic. Also, you would like your examples to be robust. If you perturb the initial conditions a little, if you have a splash and you perturb a little, then you should still get a splash. And in order to prove that, you want to perturb in a Sobolev norm rather than in some space of real analytic functions, because the world is presumably not real analytic. So one has to work in Sobolev spaces. Okay. What maybe a little bit about changing the problem. So how does this not correspond to the real world? Well, for one thing, there is viscosity in the water. One should maybe do Navier-Stokes instead of Euler. There should be surface tension. The water flows over a bottom. It doesn't. I mean, the ocean is not infinitely deep. I believe. I mean, anyone can say anything, and here I am saying the following. I believe that none of those things make any difference. And if you're willing to work hard enough, all the same stuff works just fine, and there is still a splash. But there is one fundamental thing that we're neglecting, which changes the whole physical situation, and that is that I assumed that we have water and a vacuum. If there is water and air, or let's say water and some other incompressible fluid but of very, very low density, then what will happen? And I claim just physical intuition leads to the following conclusion. So we approach a splash. The low density fluid is almost a vacuum and almost nothing changes. But these are very extreme conditions. And as we get sufficiently close to the splash, the fluid will push back. The very low density fluid will push back, and there will be a recoil. There is some experimental physicist at the University of Chicago, I forget his name, who has done some remarkable experiments. You know the movies that we've all seen. You drop a drop of milk into a smooth surface of milk, and you get this remarkable crown, and the crown breaks up into drops, which break up into further drops, and it's infinitely complicated, and so on. Perform that exact same experiment, but perform it in a vacuum. And what you find is simply that the droplet drops and then spreads out over the surface, and that's it. So it's all about the recoil from the air. And I think it would be very interesting to try to understand what happens to an almost splash singularity in the presence of some air or something that pushes back and makes it recoil.
Presumably surface tension plays a role.
I mean, surface tension plays a role, but there are, in fact, as of 2 hours ago, according to my friends on the team, this theorem can be done with surface tension. So, I mean, surface tension influences the solution, but it does not prevent the splash. What prevents the splash is the recoil from the air.
In the analytic category or in the Wilcox category?
Which? You mean the surface tension? Well, I'll email back and let you know. I don't know. I think.
But you think in the Wilcox?
I think it's well posed in Sobolev. That's what I think.
You mentioned something also about the thickness of the analyticity. Do you
Oh,
have
yes.
estimates on that?
Oh, this is for the Muscat problem. This is for the Muscat problem. We have estimates on that. Now, they're not so explicit that, wait a minute. Okay. What are you trying to do? If you're trying to prove theorems, the answer is it's all about controlling the domain of analyticity. And in particular, all right, let me take 1 minute and talk about Muscat since you asked. One takes the problem at the end when there is supposed to be a singularity and solves it backwards again. And you want, all right. So there is a domain of analyticity. I'm now not drawing the fluid interface. I'm drawing the domain in complex parameter space in which the interface is real analytic. And as a function of time, it looks something like that. And at the alleged moment, at the moment at which we think there is a singularity, it pinches to a point like that. Okay, so there is one point here at which the thickness is 0.
What happens in your solution?
This is what happens for our solution. So we take, quote, an initial condition, that is what happens at the last time when there is a singularity. It is analytic in this domain, but that doesn't mean it's C infinity because this domain has 0 thickness here. Okay, and then one follows with estimates, one follows and shows that the domain of analyticity then opens up. It opens up here and it closes down here, and you analyze with estimates what it's doing. And you check, the game is to check that you can get far enough backwards in time to see the turnover back to a graph while maintaining a non-zero thickness for the domain of analyticity. So if your purpose is to prove theorems, then the answer is yes. One estimates. One could try to do numerical analysis. In fact, we did these. I didn't explain how some of these theorems were discovered. They were discovered by numerical analysis. One can do numerical analysis on this, even in the allegedly unstable domain, because you simply follow analytic functions. And as the problem is unstable, you compensate by shrinking the region of analyticity. So in the sense of numerical analysis, also one can estimate the region of analyticity. Does that answer the, okay.